Demystifying control panels. So, I mean, a lot of you probably have delved around in the control panels. You kind of know your way around, but for a lot of people, it's black magic. You don't want to even go in there. You're afraid you're going to get electrocuted as soon as you open the door. You know, I want to go through that, kind of teach you how to navigate between the schematic that you'll see and then what's in there, so you kind of know what you're looking at, and it's not quite so intimidating. So, you know, how do we get from this to that? You know, that's the control panel, and that's get upstairs, but that's what we're going to try to go over today. Here's my one big boring slide. Safety. Obviously, this class is not going to teach you to be an electrical engineer or an electrician. Know your limitations. Don't just dive into a control panel blind and and be irresponsible. I don't want to be responsible for anybody getting electrocuted. It's just so know your limitations. Know when to call a professional to come out and help you out. How do you identify the components? What is what does a contactor look like in the schematic? What does it look like in the panel? So you can match the two. I'll pass these around when we get to that. How do you find a component that's in here in the panel and vice versa? How do you find all the instances of a certain component in the schematic? We'll kind of go over that. What are the different parts of a schematic? So you know the different sections. And then we're going to do a little bit of troubleshooting. What tools and stuff do you need if you are going to attempt to do any troubleshooting inside a panel, or even if you're talking to, say you call me on the phone, if you're asking me some questions, you can be my eyes in front of the panel. I can walk you through some stuff if you have the right equipment and tools and parts. So we'll do a couple of scenario troubleshooting, mock situations where you can, I'll show you what I would do to troubleshoot that. So first, be careful. Don't be like this guy, diving in there. So be careful. I don't, this does not make you a qualified electrician just by this, 1 hour class. So, all right, so let's get into some components. The fuses and circuit breakers, basically circuit protection. The first thing you're going to see in a schematic, generally, in one of ours anyway, is like a main circuit breaker or a fuse disconnect, something like that, and we'll show a couple examples of that. I'm going to pass a couple of these around. You can kind of look at them while we're talking. These are all the same. This is the schematic for the system that's up. I'll get one back to you. Actually, another one. We've got this is the same system that's upstairs, so probably within a couple of things. Oh, thanks. You can take a look at that one. I'll give you a card while I'm standing back here. So your main circuit breaker is where the mains power comes off the grid. This is, your main distribution panel is going to be wired to this. That's the, one of the main circuits. Obviously, we can't do on site, at our factory. So, your electrician's got to pull that in, or your contractor, whoever's installing the system. That's going to be anywhere from 120 to 480. We do stuff overseas as well. I've seen 575 and different voltages, but that's going to be your mains power. It could be single phase, 3-phase, whatever's supplying the power to the skid. That's what you're going to find there. I'll pass around with these breakers, but that's the symbols. Now the MCB, you all might also see that listed as a miniature circuit breaker, which that happens to be, but that's not what we're referring to it as when we say MCB. But so also inside the panel, you notice that there's a tag by each component. Most of the time you'll find that. That's another way you'll find the component from the schematic, how to find that in the control panel just by the tags. And we do most of the time put the tag on the panel instead of the component, because what if you have to replace that component and then the tag is going to go with it, probably, if you can't get it off. So, look on the back panel. Sometimes they get hidden a little bit behind wires, so you may have to look around some wires because once they tag that and then they wire it all up, you might get blocked. So another example of mains power incoming connection. This is a fuse disconnect. Fuses are great. They're, in a lot of cases, they're better than breakers, but I think everybody would agree if you have a fuse blow and you're trying to get your system running, you'd rather fix the problem and flip a breaker back on rather than trying to go hunt for a fuse. So we don't usually use fuses too much anymore unless a specific application calls for it. You can get higher short circuit current ratings and stuff with fuses, so there are some times where we need to use it, but This one happens to have a through-door disconnect bar. So when you shut the door, it engages with a handle. So you got to turn that handle off and shut down power before you can even open the door. So that's the symbol you'll see for that. And it'll usually have a identifier of what fuses go in that device. And then your full load current will usually be on that part of the schematic as well, somewhere in that top left corner. What's the main, the FLA, the full load amps. That's what FLA stands for, the full load amps of that system. And then what the mains voltage is. From there we get into the branch circuit breakers, which can be the same kind of breakers you've seen in the main circuit breaker. It could be single phase, three phase, depends on what you've got. Like this 3 phases would be going to like a pump, for example, or a single phase might be going to the oxygen concentrator. This one has something a little different. You'll have the auxiliary contact on the side. Most industrial circuit breakers will have this an option for auxiliary contact, and that will be labeled with the same indicator or tag name as the circuit breaker because they work in tandem. And what that's for is so that you can give a status for that breaker, whether it's on or off, to a PLC, so you know if that breaker is tripped or not. Because otherwise, if that breaker trips, you may not even know it. You know, the PLC may be saying turn on. The actual contactor may even turn on, but there's no power going to it because you don't know the breaker's tripped, so you would be troubleshooting that. But so that's what that auxiliary contact gives us the ability to watch for that. And there are other ways to do that with relays and stuff, but that's a real simple. You just snap it onto the side, and then you've got the auxiliary contact. Just like on the main incoming power, you've got potential to have branch fuses. We don't have any of these in this one. I just wanted to point out, you know, there's all different shapes and sizes of certain fuses. You just gotta, you know what they look like. Different symbols you might see for a fuse. They'll also have a tag for what the rating is. That's another symbol you might see to indicate a fuse. All right. Then we get into the DC branches, DC circuit breakers, DC power supply. Almost every industrial control panel anymore is going to have some 24-volt power inside of it. And you're going to have some sort of a DC power supply. This particular one will take 100 to 240 volts. We have ones that will take 3-phase 480 power and convert 24 volts. It just depends on what your mains power is in your box. There's some, let's see, where's that? There it is. Here's an example of one of these little blue circuit breakers. Just if it goes off, it pops and goes up, and you can reset it. It's actually just a standard, almost like an automotive type ATC fuse is where the plug will fit. Those come in all different ratings. They go on a base that allows you to just line them up however many branches you need. And they're quick and easy to identify if it's stripped or not. This is a pretty cool device that we use as often as we can. Lately we've had a little bit of supply problems like everybody else is fighting with, but this is not a power supply. It is a electronic circuit breaker module, and they're really awesome. This one happens to be an 8-channel unit, but you take your power supply and you feed it into this, and then you have 8 different channels, and you can adjust each of these channels for anywhere from 0.5 to 10 amps per branch. So if you add a device to that channel, you can readjust that circuit breaker module, reset it, and then now you've got a 10 amp breaker or a 4 amp breaker or whatever you need. And that will go from green to a red light or blink. If you're getting close to the amperage limit, it'll blink. So they're very intelligent circuit breaker modules. They're really awesome. Yeah, we've probably got little current transistors in there that monitor current for each branch. They're pretty awesome. And then they've even got status outputs you can send to a PLC or something to give you an indication when you lose a circuit breaker or something, or if there's a fault. So they're pretty nice. I couldn't tell you off the top of my head how they cost comparison, to just some standard breakers, but we use those as often as we can because they're so valuable for having that information and so easy to readjust. You don't have to buy all these different breakers. You just dial them into what you need, and it's a one-stop shop. You just drop it in and set it. So those are pretty awesome. Quick point out on this. Sometimes you're in need of a breaker. I just wanted to make sure you understand, do not ever take an AC only breaker and try to use it on DC. Some people assume DC's easier, safer, because you can touch it and doesn't do anything, but DC power arcs a lot more when you try to disconnect it. So if it's an AC only breaker, it can't extinguish that arc, so you can get fires and all kinds of stuff. Even a fairly low DC voltage can arc larger than a higher AC voltage. So when you got that 2-pole, if you see, that's the breaker that's on there. It's got this little 48 volt DC at the DC symbol with the straight line and the dotted line. If it doesn't have that, don't use it on DC. And usually see some kind of rating on it, but contactors. So these are what's going to switch your mains power to your motors. Your ozone generator is going to be turning on and off with a contactor. It allows you to switch large loads with a very low current, like right out of a PLC or maybe a pressure switch or something. Can switch on that contactor with a really low power and switch a 100 horsepower motor. Those are usually use some soft starts, but you get the idea. That allows you to switch a very high powered device with a very low current. So there's a couple of different examples. Most contactors have 3 main contacts on them for the 3 phases. You don't have to use all 3. They don't care. It's just a switch basically. And then they'll have an additional set of normally open contacts you can use to signal a PLC that the contactor's turned on. We sometimes use them to switch other smaller loads. Usually the load capacity of that extra contact is not the same as the other 3, I think. I have to check on that one. But and then you've got, almost all have a snap-on additional auxiliary contacts, normally open or normally closed, that you can snap onto them if you need more contacts for turning on different things or giving statuses to other devices. Then you get your overloads. Overloads just prevents you from, just like the name says, overloading a motor. If the motor's drawing too much power, because it's, there's a, something, a rag or something got sucked into your pump and it's running too much load. It works a little differently than a circuit breaker. It's protecting the wire from short circuits and things like that. The overload, if it's just a slightly higher load where the wire and the motor's getting hot, it'll detect that and that's what'll trip it. They all have most of them have an adjustable range, so you can get, one overload will handle a variety of different pumps and sizes. You can switch them on and off for different trip scales. Different kinds of pumps need different trip scales, and they need if it's a high inrush on a certain pump, it may need a different trip scale so it doesn't pop it immediately when you try to turn it on. I'll pass a couple of these around. In the schematic, this is what you'll see. I'll start that one there and go this way. That one's got an overload on it. So in the schematic, what you'll see is the coil. This is what energizes the contactor and makes it pull in. That can be very low current. It can be 12 volts, 24 volts DC. It can be 120 volts AC. Doesn't really matter what the voltage is. They have all different sizes. But that's the small current that's going to turn this system on. That's a typical symbol for your M1 auxiliary contact. And this is what you'll see for whatever mains equipment it is switching. You'll have your main contact, and then that'll go right into the overload. Sometimes those overloads can be separate from the contactor. This particular example, they're mated, and we try to use that one just so they're right together, but you can put them separately sometimes. But it's important to note that each of these symbols is separate. They can be on completely separate pages. So you're rarely going to see a contactor or a relay or something with the coil and the contacts all in the same section, because you're going to have a PLC page that's going to have the contact, the coil, what's turning it on, and then that's going to do this on a totally separate page. So learning how to navigate between these on the schematic is important, and that's what we're going to kind of go over. And real quick on this, I want to point out, if you see a dotted line around a device, that indicates that it's outside the control panel generally. So, anything in the control panel won't have that line around it. Then we get into the control relays. Very similar to a contactor. Pass a couple of these around. There's a dual pole, dual throw. We'll talk about those on the next page, but this wide one has double contacts. This little narrow one only has a single contact. So like I said, they're very similar to a contactor, except they don't handle as much power. They're not generally for larger loads. They are limited. Usually most of these types of relays are limited between 6 to 10 amps, whereas on a big contactor you can do 20, 30, 40 amps or more quite easily. The coil is very similar. Could be AC, DC coil. This one I'll show, this one happens to be a DC relay, and they are polarized, meaning you've got to have the plus and minus on the right terminals or it won't work. This one has a little LED lamp that lights up when you give it the proper power and it energizes the coil. So that's on the top of the relay. On the bottom of the relay, you'll have the actual contacts. So one other difference between the control relay and a contactor is that you've got both normally closed and normally open contacts. You don't generally see that except for on the auxiliary connections on a contactor. They're just normally open and they close when you turn it on. With a control relay, you often need to go between normally closed, normally open to get the right status that you need for a PLC input or something like that. So we'll go over the terminals in a bit here, but these will be your common terminals. Those if you're not energized, those top ones will be connected to these bottom two. When you energize it, now the top two are connected to these center two. So that allows you to toggle back and forth. And again, these take literally microamps or milliamps to engage these relays, but they can handle up to 10 amps or so. And obviously with any relay or any part, there's a huge range of capacities and power. There are a lot of relays between here and the big contactors to give you different power ratings for control relays as well. But these are the ones you're going to see most of the time in most of these panels. And there's your good old ice cube relay. Don't see those as much anymore, but they're still out there. It's a lot of the older control panels. You'll see rows and rows of those. So in the schematic for control relays, you're going to see this. And again, it's like the contactors. These are rarely going to be all on the same page. They may be on the same page, but they're not going to be right next to each other. Like for example, this is a symbol what the whole relay would kind of look like if you were to just put it in one spot, but it doesn't usually make sense to try to show it all in one spot and run all the wires to it to your different devices on your schematic. But so you got your coil, and there's an example of a normally closed contact, and when you see that line, that means that with no power to the coil, that's connected. And then you've got your normally open contact here. So these are the standard numbers or terminal numbers in that relay that you'll see there, but if it's that little skinny one would just be a single pole dual throw, so you'll just have those on the contact side. If you got the fatter one over there, the wider one, you'll have all of these contacts. There's just another example of way you'll see it drawn in a schematic where you've got, instead of having these separate and different parts, they'll put them both there. That happens to be on a customer connection page, so you can see what you can tie into whatever state you need, you can tie into it right there in that one spot. One more on the relays. This one I included just because it's a little bit of an unusual relay situation. This is the one that's in the Ozone generator, and most of our generators will have this if they're a PTI-based generator that has the PTI inverter. Even if it has our cells, if you're at our skid, you still have that long silver tube. We do some larger generators with still using the PTI electronics, just not the PTI block like the little 50 gram has. But this relay is what's called a soft start relay. I just included it, and I'll kind of talk about how it works, because this might be one you might have to actually bypass at some point, if that fails. But it's got a resistor on it. That blue thing is a resistor. So how the soft start works is when you first energize the mains, the contactor closes, you got mains power coming in here. For the first, it's probably microseconds or milliseconds probably. Power goes through the resistor first while it charges up the big capacitors. You'll see two tall capacitors on the inverter board. It charges up those capacitors, and once they get up to power, there's the PTI. You don't see it on there because it's underneath the chassis, but there's a DC power supply in there that powers its own circuit board. Once that gets up to charge, that relay turns on and closes, And then power is taken over by that relay. That's a 5-volt relay. It's powered by the 5-volt bus of the PTI. So then power goes through that relay, and it doesn't go through the resistor. And I explain all that because it's not required to turn the generator on and off. It just merely extends the lifespan of your generator because you're not shocking those capacitors, because they'll take as much current as you'll give them to charge up. So we charge them up slow. If a scenario happened where that relay failed, all the power is going to try to go through that resistor until it smokes. You know, they've actually updated the firmware on the PTI inverters to better recognize when something like that's occurring. I'm not sure how they do it or what algorithm they're using, but it does have a stop-start fault on it, and it'll tell you when that happens, when it'll shut off. If it doesn't, and that keeps running current through that little resistor, it'll just smoke. It'll turn into a little charcoal briquette. It's a little black crispy thing, so it won't work after that. If that does happen, you could theoretically just bypass the whole resistor or that whole relay assembly and just run it straight through. All that's going to do, if your system has a frequent hard shutdowns where you're powering it off, powering it back on multiple times a day, that would just shorten the lifespan of your inverter. But if your system just runs 24/7 like most of them do, it's not really going to be a big deal. So while you get that, you know, the parts replaced for that, you could bypass that and just let it run. That might be something that we might walk you through on the phone if that were to happen. But you would see that. It should be a nice shiny blue. If it's not shiny blue, it's it's gotten smoked. That's it for the relay. Any questions on the relays? All right. Pilot lamps and LEDs. If anybody's got any of our equipment, you know we like LEDs. We like the bling. And that generator upstairs, you see that lights up all blue and cool when it's making ozone. Here's a little example of a pilot lamp. I'm sure you guys have all seen one of those, but I'll pass it around. So they can be all different voltages, 5 volts, 12 volts, 24 volts, AC or DC, 240 volts, 120, doesn't matter. It's just to give you an indication that something's on. You're generally not going to need to do any troubleshooting, you know, with an LED per se. There's not, if it doesn't work, you just won't know that that device is on maybe, but once you verify it, you're not going to have to bypass an LED lamp or something like that. For our LED strips, I don't know if you got a glimpse of it, but we just get rolls of these strips and we can cut them into whatever length we need for whatever size panel. And then we have usually red and blue, so if you're looking at it from across the room, it makes it really easy to see the status of your system just by checking it out. You see it's lit up blue, and then we usually use the clear front panels like you see in our generator upstairs. So you got a nice blue glow. And it usually looks better in your pump rooms because they're usually kind of dark and it looks pretty neat. But if you get a fault, like an ambient fault or some kind of a pressure fault, flow fault, something like that, the whole panel lights up red. So it's real obvious, you know, more than just a little red lamp. It's pretty cool. So we like that bling. All right, so in the ozone generator, we got various gas flow switches, water switches. Often in our schematics, we like to draw a picture of what the thing looks like. I mean, I'm sure for you guys, for our manufacturing guys, sometimes it's easier if they can see what it looks like. So we don't always use a little cryptic symbol like that, you know, a true schematic symbol. Sometimes we'll just draw what it looks like because it just makes it easier to see it and know what it is. So, you know, that's not going to be some sort of an industry standard schematic symbol, but in this case, you can tell what it is. And they'll usually have a part number on it indicating so you know what it is, and you can find that. But since it looks like that, it's easy to track down. We do still sometimes use the actual industry standard symbols for a transistorized switch is what that is. But you can have relay contacts. You can what's called NPN, and we'll talk about these a little bit more later. But there's an NPN, there's PNP. Those are transistor outputs. Then there's a relay, which sometimes you require because it's a dry contact. The NPN and PNP actually put out a power, so they can only go to like relays generally. But we'll talk about that more in a bit. But our flow switch is just a loop that goes around the flow meter, and if that ball is breaking the little beam of light, then it knows you don't have any gas flow, so it triggers that off. Another example of one we actually spent the time to draw it like the actual thing. This one apparently we just got lazy and made a box with 4 terminals on it, but they both have the same wiring pinout on these two devices. That's kind of an industry standard for this sort of, I can't remember the code name for it, but it's a kind of a standard electrical cord color code. Here's an example of a PNP. That other one was an NPN, and I'll talk more about that later as well. But so here's a PNP, and what you can tell, the PNP puts out a positive output. And this is important because if you're going to try to bypass one, you need to know what it's doing. So you can see that black wire there is going to terminal A1. And if you remember on the relay discussion, A1 was the plus, and A2 is the minus. So that one's going to be getting 0 volts or negative on your DC. And then this one is going positive. So when that relay and that pressure switch detects your pressure's good, it's going to give you a positive output, turn the relay on. And then this one's pretty much the same way. That one does have also an analog output, and then we'll talk about where that's going. Now, if you've noticed, a lot of these devices have a little link number there. What that link does is it tells you what rung number on the schematic that its associated component is with, and we'll talk more about that in a minute as well. Electronic regulator, you'll see a part number. This, again, it's just a standard square box. We didn't take the time to draw that one out, but this is in our ozone generators. It's just got 24 volts and 0 volts, and it takes an analog signal from the PLC to tell it what pressure we want. You just dial in a number, I want 10 PSI, and it'll make 10 PSI. So in the old days, not that old, but recent old days, we would have a mechanical regulator, and I'm sure you got tons of regulators around. If you wanted to adjust your gas flow, you turn the gas flow up, your pressure is going to drop. Turn the gas flow down, you're going to increase your pressure. So you were constantly trying to balance that. If you ever made an adjustment, you had to do both. With this, you want to adjust your pressure, you just dial it down to 5 SCFH, and the electronic regulator will automatically compensate for that and keep you right at the pressure you want. So it makes it a lot easier to just, and we know that you're going to have the right pressure because it's pretty critical on the ozone generators that you keep the cell pressure where we want it. Signal duplicators. I got an example of one of those. There is one of these in that skid upstairs. Sometimes you need an analog signal in more than one spot. So what this will do is it'll accept an analog signal coming in, and then it'll split it to 2 different devices. It could be a PLC, it could be an outside supervisory system or a SCADA system that's monitoring the system. This one happens to be for ORP. So the customers that buy this one have another supervisory or a logger that logs the ORP value. So we bring that in, but we also need it on our skid, so we had to split that to give it to give the logger a signal as well as control our generator. Because our ozone generator has a PID input that we were talking about earlier that will ramp up and down, or you can just have it on-off control, whichever you prefer, but we need to have that that signal over there. So.
Is that what you would use if you wanted to add LEDs for information?
Not sure I follow you.
Like, if we don't have LEDs like in our panel now, but I want to add them, like how would I land those?
Like LED strips or just a lamp, or either one? It wouldn't be from an analog splitter. The analog is a variable control signal, so you can see like a value like for your ORP goes from minus 999 to plus 1,000 or something like that. That's what this is going to do. And if you would just need an on-off signal for that. And usually you're going to have, like for ours, the blue one is off of an ozone running, just an on-off status thing. So if you have a contact that turns on whenever you're making ozone, or whatever the parameter is you're trying to do, it just closes the contact. If that relay, let's say you've got one of these relays and both the contacts are being used up, you could add a second relay and just parallel it's the same voltage. You could just run 2 relays in parallel, and then you've got 2 additional contacts you can use for whatever you want. And you can hook up some lamps to that. But the analog splitter, this one actually, so what we've done here is we got the 4 to 20 coming in from the Signet ORP. We're actually using channel 1 output for our ozone generator, but which we'll talk about in a second. We also have a telemetry system on this skid, which will email you if there's some parameter out of whack. Something turns off, you get an ambient fault, it can send out emails and stuff. So we need that ORP value also in the telemetry system, because the customer can dial in if it gets above or below whatever ORP value you want to set. It'll fire you off an email or a text message to tell you your ORP's out of whack. So what we've done is we've actually got 2 devices in series out of this loop. So we come out of this, we go through the ozone generator first, and then back into the telemetry system. So you got 2 devices in series. Now you can sometimes do that, so you would think that could just eliminate the need. Why do you need a splitter if you can run just devices in series? But you can't always run them in series. Like if you've got 2 ozone generators, if they were both on all the time, you could get away with running them in series. But if you need to service one and you turn that generator off, now you've broken your loop and now the other one's not going to work. So in some scenarios like this one, we're always going to have the telemetry system on when that generator's on. So that one makes sense. You can have those tied together in series. This one isn't generally used unless the customer wants to hook it up to their logger or their ACS system. Too much talking this week. So here's the back of the Signet ORP monitor, or could be anything. The Signet, the same 9900 will do flow and ORP, pH, whatever, but we're using it for ORP. It's another one where we've pretty much just drawn it to look like the actual device. Got your preamp hooks up there with that type. We've got the wires labeled so that's obvious if you need to figure out what wires go where. We got the colors. Got your main power coming in off the branch. Now this one, here's the 4 to 20 loop. Now there's different types of transmitters. Some will have powered, where they power their own 4 to 20 output. This one does not. You can see where we're feeding it 24 volts from the DC power supply in the panel. And then your actual, it's kind of deceiving if you're trying to figure out loop plus, loop minus, because they call it loop minus, but this is actually the positive 4 to 20 going out. So you would hook that loop minus to the positive of your PLC input. So it's kind of confusing if you're not really sure how to read that. But anyway, so that's what you'll see, you know, in the panel versus in the control schematic. We'll talk. This is a telemetry system I was talking about. We're using a Sensiphone. I don't know if you got any experience with Sensiphone. They've been around for years. You know, from old dial-up little transmitters that would call a regular phone, and I don't know what they would do, give you some kind of beep tone or something, I don't know. But or I think we did one years ago that you just recorded a message to it, and it would just call you and just say whatever you said. But it was just like a single input that would trigger that thing to call you. This particular one is it's a little newer one, but they call it a Web600, but you hook it up to your Ethernet, to an internet connection, and it's got 6 different inputs that you can reconfigure to whatever you want. We happen to be using them for ambient ozone, which is just an on-off contact, dissolved oxygen, which is an analog input. What's this one? Ozone running. I think that's ozone running. Ozone running is just a relay contact, then ORP, and then a pressure sensor, that one that's down right before the backflow, if you remember the picture. And then, what's the other one? There's an ambient one in here. Water flow. Oh, ambient was down here. No, that's water flow. Can't see my thing very good. But anyway, each of these outputs, you can make it an analog signal or a relay signal. You can hook up temperature probes to it. And then within the programming for that, you can set up, if anybody saw the demo up top, we pulled up the little graphic on the computer to show you what it looks like, but pretty neat. The other thing you can do is, if you've got different technicians on call at different times, you can actually pre-program in there who's on call at what time, so you can have different emails. It'll send it out to, you know, this guy on the weekends, he's on call on the weekends, or you're on call at night, or during the week, you know, it might be you. You can have it automatically divert the messages to the right person at whatever time you want. So it's a pretty neat little device. Part of that telemetry system, there's a backup battery. So if the system turns off, you actually can run it for a little while. It'll still communicate, send out those messages, as long as of course your internet might have crapped out too if the power goes out. But if you've got backup systems on that, it may still be able to get out. But it does have some data logging too, so it'll continue to log that information while the power's off. And then this is just a pretty basic Wi-Fi access point, how we get the connection. We were getting reports, a lot of the customers don't have wired Ethernet down to the ozone room or whatever you're at, but a lot of them had Wi-Fi, so we put this on there to give you the option. You can just set that to receive your Wi-Fi signal and then convert it to the Ethernet cable, and then it just runs right into the Web600. So you don't even really have to get too involved with your IT people if you don't need to remotely access into it. Like if you don't need to pull that interface very often, as soon as you get an internet connection, it'll shoot emails off. So I know some people, some of your internet IT departments are kind of finicky about opening up any kind of ports to come in, but if you just need to send an email out, it'll do that right out of the box pretty easy. There is a couple of antennas outside the box because this is a steel box, so you won't be able to get a signal out. So we put some bulkheads on there, and when you receive this one, you have to install the antennas on the outside once you get it, so they don't get broke off in transit. So later on in the schematics, you'll see manufacturing wiring or customer connections. Roughly the same thing. If you were mounting these things yourself on the wall, these are things you would have to hook up to the panel separately. But since this is an all-in-one skid, our manufacturing team uses this to know how to interface all the different components together that are pre-mounted to the skid. You can see your control relays there. You can see how we've used those. We're using the normally open on that one, normally open on that one. This one happens to be an analog signal coming out of that splitter. So actually comes out of the splitter, goes out to the generator, and it comes back, and then it goes over to that telemetry unit. And then you got your customer connections. These are ones that would generally not be populated when you get it, because you can hook those up to a supervisory system, ACS, SCADA, whatever you want to call it. But statuses for various things, and these are generally the terminals you're going to see that match up to these things. Now that one looks like it's just going right to the actual M1 contactor, but sometimes we'll try to draw in actual terminals so you know what you're looking for. These could be inputs or outputs. That happens to be an input. So if you have the pump in auto, it won't start unless you give it an outside run signal. There's some more examples of some customer connections. These are all relays in the generator. If you needed to see a specific status of something, you could tie it into these relays to give you, this. So for ambient ozone, for example, if you get an ambient ozone fault, that relay is going to trip, and you can get that signal to another panel. The generator schematic does have a legend, so you know what relay does what. You can see it here, but it just makes it a little easier to identify what relay's doing what. And that helps for troubleshooting, because you can, even if you don't see something on the HMI, you can open it up, and if you know what relay is supposed to be turned on in what scenario, you can at a glance know what the status is. No, they don't. These, if you needed to turn it off, you could. These little orange things are a little lever. You can actually do it on that one if you ever pop that out. But these relays, you can pop out so you don't have to replace the whole base if something happens to your relay. You can just push this little lever over, and it'll pop the relay out, and you can replace that if the relay has failed. You burnt the contact up or something. But no, they don't have a bypass. We'll talk about kind of some of the troubleshooting stuff and what you might need to do, and jumping around relays is one of the things you might have to do. I'm trying to think if I've even seen any with a switch. I don't know that I have. I'm sure there's some, but not very common. Just some more examples, digital inputs. This is on the generator. These are going to be pre-wired, since this is an all-in-one skid. This stuff's already pre-wired. That one, can't remember if that one's pre-wired or not. Some of these, if we're not using them in the system, and even if we don't know if you're going to use it or not, we'll often ship it with a little jumper wire in some of these, because it won't turn on unless you have that installed. So if you do need to use that, you'll just pull the jumper out and hook it up. Just more examples of the customer connection pages. There's your terminals that you'll be looking for if you're going to hook up a outside analog signal. This one in this case is already hooked up because it goes over to the main control panel. That's that one that loops through there and then goes back to the telemetry system. Handoff auto switch. Show you guys tons of those. If you've ever seen it in a schematic, this is kind of what it might look like. In the auto position, it's looking for an outside connection to close that loop, so it'll turn on. If you have it in the hand, it just ignores that outside run connection. So that's the only difference between hand and auto. Whatever other parameters are required for that device to turn on would be the same whether you're in hand or auto. Our ozone generators have a built-in ambient monitor. That's one of our, it's actually an OEM 3, it's not an OEM 2 anymore. The same layout. Some of you might have some older ones that are OEM 2 still. If you need that, they don't sell that sensor anymore, so we would just replace it with the whole board, but it's just a drop-in plug and play. The terminals are the same, the layout's the same, just has a different sensor. But you can see they label it AC or plus. This one actually will take an AC power input because it's got its own built-in little rectifier, but we use it in DC mode all the time, so it's got 0 volts here and this 24 volts here. But the terminals in the schematic and how you identify what terminal it is, these are fairly obvious because this is another one we've kind of drawn it to what it looks like, but can't see it in the picture. But we'll say TB3 near it. That one will say TB1 up here. That's the relay output, so when it's tripped or not tripped, it opens and closes that relay. In the generator, if you look inside of our generator upstairs, it's on the left-hand side on the side panel. Right below that, we have an oxygen concentration monitor. So you can just continuously monitors that oxygen concentration coming out of your air sep. So you always know what you're making. It is good to spot check that once in a while. We like to offer our customers a handheld oxygen meter, so you can do spot checks. So if you don't have that, you got another system, or you can just double check that that's still accurate, because like anything, things got to be replaced once in a while. But if you suspect that value is incorrect on your screen, you can double check it. But anyway, so this is what you'll see on that. You can see they have a 9-pin serial connector. I don't know if you're familiar with computers much, but that one's kind of a pain to connect to. So we supply a 9-pin serial to a terminal breakout little board for that, so you can just wire it right to terminals. If you remember, that was on the pressure switch. There was an analog coming down off of that one. This is where it goes, and what that does is it compensates for pressure differences. So your oxygen concentration will be whatever at atmospheric pressure, but as the pressure goes up, because we've got this sensor in a pressurized gas line, the oxygen line, that compensates for that. So we always get an accurate oxygen value based on whatever pressure is in the line. So if you change your cell pressure from 10 to 20 psi, if you didn't have that analog line to tell the instrument that, your number would be a little bit skewed. It wouldn't be accurate. So that's what you'll see on the inverter. That's obviously the PTI 50-gram inverter block. We've drawn that one out to look like the actual unit. Let's just see about that one. And then obviously some things are pretty self-explanatory. Enclosure fan, it's pretty easy to spot that one. It'll give you the power for that. If you looked at the branches, you could tell what voltage that was. I think in this case it's a 24-volt fan. Our generators will have a cabinet temperature. We actually have triple redundancy temperature monitors in our generators. The actual PTI inverter has a cell temperature probe on it, and it has a heat sink temperature, so it's monitoring its own temperature all the time. So if it gets hot, it knows it's smart enough to try to ramp it down to keep it from overheating. But we added this cabinet temperature so we can tell, if the cabinet fan stops working, we can pretty quickly, or if maybe you're not cleaning your filter often enough and there's no airflow going through it, it's getting super hot in there. And you can actually see that temperature on the home screen of the HMI. But it's a little bit covert. You don't really see it much. This one happens. Usually you don't see the wire that long. It'd be a tiny little. If you recognize that, it's a little transistor. I can't remember the name for that housing, but it looks like a tiny little transistor you would see on a circuit board. But that's all the size it is. It's got 3 wires coming off of it, and we usually just stick it out of the pan, do it somewhere to capture that cabinet temperature. What you don't see here, if you follow that wire in, on the inside, we just bury it in the panduit somewhere, but this is a 5-volt sensor. So we have a little DC to DC converter in a piece of heat shrink that's just buried in the panduit somewhere that converts 24 volts to 5 volts for that sensor, but it still does go to these same power points. That's your 0 volts, and there's your 24. Briefly on this one, so this is our analog signal coming out. If for some reason that sensor fails and it's reading too hot or too cold, or it wouldn't be too cold, but if it's reading too hot, you can actually disconnect that wire and it'll just go blank on the actual input, because we've got such triple redundancy on the temperature. It's not going to be catastrophic if you lose that while you get it fixed, so you can just pull that out, because if it's faulting, as soon as you turn it on, the thing says 150 degrees or something because that sensor's failed. You can just pull that wire out, and that's something we could walk you through on the phone if you're having that issue, but just so you know, it's, you know, with such high redundancy on the temperature monitoring, it's not catastrophic to pull that out while you get a replacement sent out. The PLC, we use these little IDEC all-in-one HMI PLC units. This one doesn't have the analog cartridges in it that you see there, but pass that around like you could add it there. We use that in all of our standard generators. We call it our Smart Series generators, because we've just basically loaded the thing up with every bit of information that we can gather so that the thing can run safely. It monitors its pressure and gas flow. You know, if it's a water-cooled unit, it'll monitor that. So we always know that the parameters are safe for the generator. So too many manufacturers will just sell you a generator. It doesn't have any safeties for pressure, doesn't have any safeties for water flow, so it doesn't ever know if there's a parameter out of whack. So there's very little. We wanted to make sure everything's covered, so you know you can't basically dumb it down, so you can't accidentally just run it into the ground and burn it up unless you bypass too many things. So, but you got these are analog modules, and we'll talk about some analog troubleshooting and testing a little later. But see the V on there? That means this one's a voltage signal. This is a current. So if you heard of 4 to 20 signals, that's these current ones. And this one has voltage as well. So a couple of the devices, like the PTI, has a voltage output that sends back to tell us how much ozone it's making. And then in the schematic, this is another one we've drawn to look just like it. So it's pretty, can't miss that one. It tells you exactly what's wired to what terminals. It tells you what that terminal's function is. That's what you'll see. You can see where we're hurt. The contactors there, you can see we're turning on relays with these outputs. Now, these are relay outputs, so you really could control some of this stuff directly with the output from the PLC, but in order to avoid putting in any undue load on the PLC, we'll almost always take even a relay output to another outside relay, because it's a lot easier to just swap a relay output than change that whole PLC if something happens and somebody fries that relay. So this one does have a couple of analog outputs as well. All right. And just a couple other examples of analog module. This happens to be a Siemens module. We make a system for Modelo beer, and they require us to use a Siemens PLC, so that's a little example out of their schematic. So you'll see a lot of different types of modules in your diagrams for different systems. There's another example. That one's also a Siemens output module. Transformers. So this one's on our skid up there. The AirSep on that, this is a 3-phase 240 volt system. AirSep only makes a 120 volt version of that AirSep Topaz Ultra. So we have to create our own 120 volts. So we put this little step down transformer on there. And again, you get the dotted line, means it's mounted outside the panel on the back side of the skid. You could also have transformers inside the panel. Looks something like that. That's just to create the control voltages. Sometimes you need a control voltage of 120 volts or whatever. You'll see them both. But they always have this on the diagram symbol. We'll always have a couple of coils. They'll look different depending on the transformer layout. This particular one has different taps for different voltages if you're running at 240 volts versus 208, so that you always get the voltage output you want if your mains voltage is slightly different. All right, that was it on the components. Any questions on the components? Whoops. Nothing? Okay. we'll go a little bit into the navigation of the, I'll borrow your schematic here. So the way we lay our schematics out, which is kind of the standard I've seen, is your first few pages are going to be your incoming main power source, AC power distribution, so all your main power coming in, and then the different branches are going to branch off of that. Go to your pump. There's the ozone generator, transformer, then to the oxygen concentrator. All that power distribution is going to be on the first section. DC power supply. From there, we get into like the DC power distribution, all the DC components, relay, logic, control circuits are going to be following that. Instrumentation, all that stuff that's DC powered generally is going to be right after that. This first section doesn't really have any PLC stuff. It does have the telemetry, but if you have a PLC in there, you're going to kind of get into the PLC logic on that. If you go to the back section, you'll see it on the ozone generator. It does have that more of that layout where you got the PLC showing on there, but all your digital I/O, analog I/O modules. If it's got an Ethernet network tied to that, you'll kind of see that architecture. And then towards the end, you usually see the customer and field connections, things like that. Sometimes we'll include a bill of materials on the schematics. Just depends on the system and the LSS specifications if they've asked for that. We've already kind of gone over this, but I wanted to kind of give you this overlay to show you how these little tag links work. So, oops. So here's our CR2 coil that sits on rung 225. Now the rungs are based on page numbers. So we know the 200s are on page 2, 300s are on page 3, 100s, so forth. And then the last of it is basically that rung on that page. So the coil for that relay on rung 225, and it's linked to rung 217 and 233. So if you go to 217, there's the coil or the contact for that relay. And then 233, there's the normally closed contact for that relay. And for example, like here's CR3, it's got its associated part on rung 313, so that'd be on the next page. You'll find the coil or the contact for that. You guys can probably find that on the schematic you've got. This is out of that, but this one, its associated part or contact is on page 409. But so that's one way to find the different pieces, because I told you they're all spread around the whole schematic. You can find the coil and the associated parts to that. So you'll never see them all bunched together, or pretty rarely. To prevent having to run a spaghetti maze of wires all over your schematic, a lot of times we'll just cut them short, and you'll have an arrow that'll have a link to where that goes. And just like the components, it'll show a rung number where you can find the other part to that. So this might be on page 1 or whatever. Those arrows mean you cut it off, and then you go to page 2, and then you can see where those 24 volts and 0 volts will then re-enter the schematic. So it just keeps you from having to draw tons of wires all over the schematic, keeps it clean. Because you might have, several dozen of those all over the schematic, where you need to make hops. I think we've covered the navigation of the schematics quite thoroughly. Any questions on that before we move on? So let's get into some testing and troubleshooting type stuff. So you're going to need some tools if you're going to get into a panel and do much of anything. And you can give it some visual inspections, but for some basic stuff, different multimeters. You don't have to spend a ton of money. I'll pass some of these around, but for 30 to 50 bucks, you can get a pretty nice meter that will have all the functions you need for 80 or 90% of the stuff you're going to do. I'm kind of a nerd, so I collect these. It's just probably a fraction of the ones I've got. Every time I find one that's cool, I'll buy it. So I actually have a meter in my pocket right now that links to my cell phone. This is the new Kickstarter one that I found. Pretty neat little units, an oscilloscope, data logger, and multimeter all in one thing that links up to my phone. So anyway, but you might want to steer clear of like the little $5 Harbor Freight meters. I mean, they'll work, but you can do better. So it's a good investment to spend 50 bucks or something on something. You don't have to spend like $700. This is like the one I'm passing around over there. It's an 87.5 or A7V. It's like $700 from Fluke. You don't have to spend that kind of money to get a functional meter. clamp on amp meter is handy. If you're measuring amps, you don't have to disconnect any wires. That makes it much safer, especially for the people that aren't electricians. You can just clamp it around a wire. You don't run the risk of getting shocked. Something like this is handy, but it's a little more advanced. It's a process calibrator. It'll actually produce a 4 to 20 milliamp signal, or read a 4 to 20 milliamp signal, but even the cheap meters like this one will read a milliamp signal. This one will produce it and read it. I got this one off of eBay, but you know, if you need to simulate a 4 to 20 signal to something, they're pretty handy if you know how to work it. But you don't have to have that. But a good multimeter, make sure it has a milliamp range in you know, AC and DC. Millivolt range is kind of handy, but you don't have to have that. They don't all have that, but definitely the milliamp range, because you guys are all going to probably have some current loops in your system where you got to monitor 4 to 20, and you need that milliamp range. Some jumper wires, maybe some longer ones, things like that. Assortment of regular hand tools. An actual small, like, terminal screwdriver. You know, you can't get your big clunky screwdriver. Those terminals are pretty small. You got to be able to fit it, you know, in the little screwdriver holes. So some kind of little screwdriver like that. You know, these two are actually electrician screwdrivers because they've got the covers over the shaft so you don't accidentally short it against something. But so what do I do if there's a problem? I'm going to go through a couple of different examples, kind of how I would work my way through it. So here's an example. This is from our schematic, actually in the system upstairs. So, and kind of funny story, when we got here to get our system running, I don't want to do a spoiler. I'll tell you after we do this, though. I don't want to be a spoiler. Okay, so let's say the pump won't start, which means, you know, the M1 is not turning on because that controls our pump. HOA switch is in the hand position, so power should be going this way. We've already verified the circuit breaker number 1 is turned on, so that's the auxiliary contact I was showing you on that circuit breaker. So that should be closed. I don't say it here, but, you know, there's the overload. So you check the overload and it's reset, that's not tripped. But just know, you know, some of those overloads, I didn't mention it, but they have, you can select automatic or manual reset. So sometimes you might actually have to open the door to reset an overload if it's set for manual. A lot of the times on a PLC, you'll actually have an input for overload. This system doesn't have that, so if it gets an overload, you're going to have to open the door and check that yourself. But a lot of them, if they have a more advanced or full PLC, you'll actually get an alarm specifically for overload. But anyway, moving on. So let's say the overload's okay. If I go into the panel and I push this in with my finger, the pump will bump over. So I've done all that troubleshooting. You know, now where do I go from there? Because it won't work. I get my meter, put it on volts DC, because I know this is a DC bus. I get 0 volts, I get 24 volts. I didn't mention this, but the way we label our 24 volt circuit breakers is we use a 24 dot whatever. You know, if it's a dot 1, dot 2, dot 3, dot 4, however many DC breakers we have, we like to label them like that so they don't get mixed up with the CB indicators. So we just want to follow the 24 volts through this circuit. We know, you know, we got to make sure first that we have 24 volts between here and here. If we do, then this should pass the power through it. So we measured each of these points, and you can find those in the schematic and then translate that either by the wire number or terminal number. You should be able to find those by navigating through the schematic. So I've confirmed I got 24 volts here. It's in hand. If I find it here, that's good. I got it here, that's good, because the circuit breaker's okay. I follow around, I got it here, but then when I get to here, there's no 24 volts. So I know CR2 is not turning on. Well, what's CR2? So let's figure that out. So same schematic. Here's our flow switch we were looking at. There's CR2. So I'm not seeing any flow. So, or let's say I am seeing flow, but it's still not turning on. You know, what do we do? Here's the example from upstairs. We got that water loop. This system actually relies on a flow switch that is normally installed in the customer's process water loop. So the whole system turns on when they turn our main process loop on. You put the system in standby. You got the pump in hand mode actually in this one. Generators in standby. As soon as this thing sees flow, because they turn on their main process flow, it sees flow, and all these relays turn on, and then that just triggers everything else to turn on. So our injector pump turns on, ozone starts, and it just comes to life. In here, upstairs, we don't have the ability to drill a hole in their process loop. They would frown on that, so we had to bypass this. So let's say that in the field you're trying to do this, and this is not working, but I know I've got flow, and I've got to get this system running because animals need their life support system. What are we going to do? We need to identify what this is actually doing. We know this. We can see that this is an NPN type. Again, we'll talk about this more as we keep going because it's an NPN and PNP is important for you to understand. So this puts out a negative signal because it's hooked up to A2. So if I just jump her from 0 volts over here over to that terminal, I'm going to turn on CR2 and CR3. It isn't going to care what this is doing anymore. So I've just simulated what that switch is supposed to do. And then that's going to turn on the system, and then it's all going to come to life after that. So that's one example, and that's a real-world thing you might have to actually do. But knowing how to figure out what that switch does and how to find it in the schematic is important. So another one, here's our ozone generator. Let's say you've got a gas flow fault in the generator. You can see the balls floating in there, but there's the PLC says you got a gas flow fault. What are we going to do about that? Anybody got any ideas?
Is that optical one, that optical switch you're saying? With the
Yep,
little
that's the one that goes around the flow meter, so if the ball's blocking it. So what do you think?
test your continuity through that optical switch basically, right?
No, because this sensor is it's an NPN sensor. So it's not a relay. So a relay, you could actually measure continuity through it. This one actually is an NPN sensor. So it's got 3 relays. It's got power and it's got an output. So you can't really measure continuity through it with a transistorized output.
So then you test your voltage on one side to
Yep, you could measure. And again, this is an NPN. You can see it's going to A2, and it actually, I just know from the part number. You can't see it from where you're at, but we should be getting 0 volts coming out of this when the thing's turned on. Getting a little more to the basic things that you would first check. I mean, there's a couple of LED lights on the thing. Let's look at the sensor, see if it's got the lights on. That particular sensor has, I should have brought one, I didn't have one handy, but it's got one power light, and it's got another LED that turns on when it's made, or it should be sending out a signal. We've looked at that. Let's say that's on. It doesn't do anything. Yeah, so we know that's a 0 volt or an NPN, or it's supposed to be. So I'm going to get my meter. Obviously, first I should make sure I've got 24 volts over here still. It's like the other one. So we can measure from 0 to 24 volts, make sure that works. But then if I measure across that relay and I got nothing, I know that's not putting anything out. So that sensor is not outputting its appropriate signal. So again, I've deemed that defective. I got to get the system running. I could just run a jumper wire from the 0 volts over to that wire, and that would turn on CR2 and clear our fault. Now I've got time, I can figure that out. Now, anytime you bypass any of these safety sensors, pressure, gas flow, water flow, you got to make sure that you're watching that daily until you get that sensor put back in there, because they're there for a reason. If you lose that, if we're trying to run this generator and you've got it bypassed, but there's no gas flow anymore, and you're just deadheading the thing, but it's still trying to run, you're just going to burn the block up, because it can't cool. You're just making ozone. Plus, ozone's going to migrate back through the system because there's no gas flow sucking it out. There's a lot of the flow meter. That stuff's not ozone safe. So anyway, just want to reiterate, if you're going to bypass any kind of sensors, you got to make sure you're keeping an eye on that until you actually get it fixed for real. But I know there's scenarios, just from experience, you're going to have to override some things once in a while. So that's an NPN. What about this one here is labeled PNP? How would we jumper out that one if that one was having an issue? Anybody know? Let's say let's say the same scenario, but our pressure's not working. We got a pressure fault. What are we going to do on that one? Yeah, it's a pressure switch looking for cell pressure, but let's say, it doesn't seem to be working, or maybe this thing just died and it's just not putting out anything to this relay. How would we bypass that one to get the pressure switch bypassed to get us back online? Can't really see it very good, but that's on the generator pages, probably back in there a ways. Better get moving on, we're almost out of time. So that's a PNP, because it's going to the A1 terminal. I know it's a PNP because it says PNP right there, but since it's going to the A1 terminal, I know that's plus. So if I was going to override that one, I would just need a jumper wire from 24 volts. So NPN, you'd have to jumper from 0 volts to the output. PNP, you would jumper from the positive or the 24 volts over to the output, and then that would trigger on that and get us going. All right, does that make sense to everybody? Clear as mud. Analog gets a lot more involved. It could be a class all by itself, but I want to go over a few specific things because I know if you're talking to me and we're troubleshooting some stuff, if you've got the tools, I'm going to try to help you walk through to figure out how to test some stuff. So it'd be good for you to know kind of what you're looking for. Since we have both, now 4 to 20 is by far the most standard in the industry, but we do have some voltage signals coming in, some analog voltage signals. We got two voltage signals, and we got 2 current signals. So you got to know how to test both. 0 to 10 volt DC analog is really easy. It's like measuring any DC voltage. You just put them right across the terminals, and you're going to see something between 0 and 10 volts. So it's pretty straightforward. You know, touching the terminals like that is not going to interfere with the system. You can do it while it's running. You're just going to see a voltage on there, and you can tell what's going on if you know what voltage you're expecting. That particular one is the bus amps coming back from the inverter to tell us how much ozone we're making. So if you've seen our generator upstairs, there's those 2 red bar graphs on the screen. That upper one is getting a response back on that input to tell us, the generator saying, I'm making this much ozone. You're asking for 50%, I'm making 50%. That's where that signal comes from. So if I want to read that output, I can do it here. I could also do it at the actual inverter as well, but we'll just kind of focus on looking at it at the actual receiving end of it. So that one's pretty straightforward. You're going to put your meter on volts DC, obviously. Analog is a little different. There's a lot of different ways to measure it. They each have their pros and cons. My preference is nearly always going to be to pull one wire out. You got to measure it in series because you got to be part of that loop, with some caveats, and we'll talk about that. But this is by far the most consistent way to get an accurate representation of the actual loop. You can do this while the system's running. You'd have to maybe turn it off and put it in there and then turn it back on, because if you pull that wire out, obviously something's going to happen in your system. But potentially, if you're doing this, maybe something's already not working, so you're having to do it anyway. But anyway, measuring it in series, and just, I don't know what these terminals are on this little graphic, but just know that some meters have a different terminal if you're going to if you're going to measure milliamps. So this one does. You're going to go from common, and it's got an actual milliamp port. So you don't want to measure it from the voltage. It won't give you any kind of reading. Some of them use the same terminal for voltage and milliamps. Not all of them. So you got to know your meter. But just I wanted to point that out. So in this case, that would be similar to this meter, since it's got the milliamp probe. So you can use a different probe port, and of course it's a different setting. But you're going to wire it in series to that, and that way, this is going to read the same thing. Whatever you see here, you should also see in your PLC, because the whole loop is one big chain. What about a clamp-on ammeter? Clamp-on ammeters are awesome. This one won't measure milliamps. This particular, and actually, a lot of them will just do AC clamp-on voltage. This one will do DC, but not really much into the milliamp range. So we do have a Fluke milliamp one in the shop. They're really expensive generally, so your odds are you're not going to have a clamp-on one that does that. You might, if you do, lucky you, they're cool. But that's by far the easiest way to do it, because like any clamp-on, you just clamp it around the wire and you'll see it. If you have it one way, it might show negative 20 milliamps. You flip it around, it'll show positive. It doesn't matter, it's still the same reading, but it just gets negative because it depends on which way it's going through the clamp. So that's a nice way to do it. They're just not as common for a meter that'll clamp on and do milliamps. So there's 2 other ways to measure it. It's not my go-to, but it has its place. If I take my meter and I've got that hooked up and it's in the milliamp range, if I put that in parallel across that, anybody know what think is going to happen? Have you ever tried that, or what do you think is going to happen? I've got a milliamps just like this. I got the wire hooked up, and I'm going in parallel like I did for the voltage. I don't expect you to answer, but I had to put you on this spot. It will probably read close to, I say I'm giving this 20 milliamps. It'll probably read close to 20 mil, probably 19 and a half, something like that. It'll read it. The drawback to that is, as soon as you do that, if you're doing it in a running system, the PLC is going to all of a sudden see 0 milliamps. Because it's got an input impedance of about, this particular one, now these range too, and this is another thing I'll get into in a minute, but this one's a 250 250 ohm input resistance. This in the milliamp range is like 1 ohm. All of the current is going to go through this. So that can no longer see any current because it's all going through the meter. So if your system is running, what's going to happen if it all of a sudden goes to minus 999 ORP? It's going to ramp up your generator if it's on a PID control. It's going to shoot up to the top. So, that could be a problem if it's a pump controller, maybe the same thing. Your pump just shoots all the way to the top and does something dramatic. So there's a place for it. If it's not running, yeah, you can do that. Depending on the input resistance of that, since we're kind of getting super geeky now, but depending on the input resistance of that analog signal, you're going to get an inconsistent number on that. It's usually going to give you most of it, but if it's a lower resistance, like I've seen PID controllers clear down to like 2.4 ohms. If I was to hook it up like that, it's going to almost split the difference. So I'm going to see, maybe 12 milliamps over here and 9 or something on the PID controller. So it's not consistent enough for you to be able to use that. If you need some kind of precision, if you need to know if you're really at 18.5 milliamps, you may not be able to get that kind of result if you just put it right across. So I rarely ever do it like that. Your other option is to actually measure DC volts. You can get a DC voltage drop across that. You can do that when this thing's running. You're not going to fry anything, but your results are going to vary. Again, kind of like the milliamp, but even more. For example, if you know Ohm's law, this 250 ohm resistance of this loop, if I put my DC voltmeter across that, if I'm running at 20 milliamps and I got a 250 amp, or keep saying amp, if I got a 250 ohm load, anybody know what voltage that is? 250 ohms at 20 milliamps. It's going to be at 5 volts. So I'll see 5 volts DC across that as a voltage drop. But they're not all 250 ohms. Like that PID controller, that's a 2.4 ohm load across, or a resistor across that. It's going to be a completely different number. Some of these are 500 ohms or 70 ohms, some Allen Bradley stuff. So they're all over the board. So if you're looking for like a specific number, like I think I should have 12.5 milliamps, and you measured the voltage across that, it's going to be really difficult to extrapolate exactly what that translates to, unless you know exactly what your loop impedance is. So again, if you just need to know if there's some sort of signal there, you can probably get some information from that, and it's quick and easy. You don't have to pull any wires off, but it's just not consistent and reliable enough, so it's difficult to get a kind of accurate reading. Very important. If I'm measuring milliamps or amps on just almost any meter, make sure you put it back to volts before you switch it to volts and hook it up to your power. You're going to smoke your meter, or you can blow the fuse, and it's not going to work anymore. I know this by experience several times. As you get busy, you don't do it. Now, the Fluke has a pretty nice feature. They don't all have this, so this might be something you get from a slightly better meter, but if I put this in volts, and I've got my meter lead still plugged into milliamps, it beeps at me. So I'm like, oh, I better not do that. But if you got one that doesn't have that, chances are you're going to go through a few fuses before you're done. So be cautious of that. Make sure you move that probe back over where it's supposed to go. All right. Look at that. Well, we went over a couple minutes, but any questions? I know that's probably, everybody's brains are probably smoking, but it's a lot of stuff to cover, and I just wanted you to kind of get a feel for a few things, and hopefully it was helpful. All right. Okay. Everybody sign the sheet. Got your emails. Make sure you wrote legibly so I can I can email you that presentation if you want.
Thank you so much.
Thank you.